Thank you, Steve, and thank you to everyone that has joined us online this morning. So today I'm presenting a very brief overview of a geomodeling workflow and what you can expect some of the resulting products to look like and how they might be used. I'm going to pass it over to Daria, who go into more depth on how to use a geomodel in reservoir simulation modeling. So first, let's remember that a geomodel is a representation of real rock properties. It's never supposed to be an exact duplicate, and that not every aspect of a rock might be relevant to the specific reason the model is being made. So I just wanted to remind people, let's take a look at some examples of the properties we're trying to represent in our geomodels on the left. In the left square, I have examples of real rocks with different characteristics that could be present in the reservoirs, but may remain undefined in the models. So in sandstone, we have iron concretions along with subtle grain size variations and erosional contacts and an alien sand that could result in different vertical and horizontal permeability boundaries. Also have a vuggy limestone that represents rock with high porosity, but potentially very low permeability through the matrix to connect those very large bugs. We have a cherty limestone that represents, a rock with discontinuous mechanical properties that would be important to our friends in the drilling department. And then finally, a real rock outcrop that shows subtle stratigraphic contacts with dipping strata on the bottom, flat lying on the top, along with cleared preferred fracture orientations. Versus what a geomodel might look like, which is on the right, which is what the agglomerated properties may end up looking like. Nothing like your real rock, but something that represents the key qualities. So what can we put into a geomodel? On the previous slide, we looked at example surfaces from rock properties, but we do use domain-specific data sets in the subsurface. So a geomodel should be purpose-built to capture the lithologic sequence, heterogeneities and variabilities, and distributions of rock properties that matter to your specific end goals for the model. Rock properties should be distributed within facies to understand how those properties vary spatially. So a geomodel can incorporate geological data in the form of depositional, sedimentary, and stratigraphic models, along with structural models. Petrophysical model that's core tide and facies analysis. Pick your favorite facies. There's a lot to choose from. Incorporate geostatistics with different property distribution methods, geophysics, which can provide structural control, property volumes, and inversion properties if you're prepared. Geomechanical data to help you understand the stress state. And finally, reservoir engineering can supply some porosity and permeability trends or alterations to your measured properties with observed trends from reservoir simulation and production. So the geomodel can incorporate different scales of data, from cuttings to core plugs to image logs, well logs, whole core, seismic survey data, survey volumes, 2D, 3D data, and finally, maybe even some outcrop data if you're lucky, or if it's something that you can incorporate into your model and relevant. So why go through all of the rigor to make a product that is only a representation of the subsurface and not an exact replica? Well, it turns out you really don't need to replicate the subsurface to understand it or create a model that's useful in answering your particular questions. Your understanding of the subsurface can vary depending on the model's purpose. Common modeling outcomes are built to answer questions about reservoir simulation, rock property evaluation, high grading acreage and sweet spotting, geosteering wells, competitor acreage and well analysis, geobody mapping, specifically if you have seismic data or very dense well data sets. And finally, the geomodel can be a repository for spatial data. So a geomodel is most useful before any wells have been drilled and most accurate after the last well in the field has been P&A'd. Obviously, that's not very practical. We need data to put into a model, and we also, have to have a use for the model. So doing it at the end of the life cycle isn't very useful. So most geomodels are built to pass along to a reservoir simulation or stimulation team, completions engineering, at some point after initial data has been collected, but many wells have yet to be drilled, so that the solutions or solutions from the model can be employed in the actual development of the field and alter a path or alter a plan for the company's drill plan for acreage. So Specifically, a geomodel might be really useful for planning well spacing and well interaction between parent and child wells. So something to consider in the process is the amount of time it will take to build a geomodel. Obviously, this is very dependent on the size of the data set and what data are available to use and the state of any existing interpretations. I have an example of what a large data set with a few hundred wells might need time-wise. So, and again, any basic geological modeling like basin modeling or developing a new sequence stratigraphy will add a lot of additional time. So, budget the time. I have at least 3 months to take a project from a raw start to a finish, given a decent amount of initial kind of geological work, and you understand what the questions you're trying to answer are. So you also need to think about what needs to be considered at the project onset. Do we already know, about the model? Can I use an existing model? And what stratigraphic section needs to be included? Data density. There's kind of no one fit for all purpose reservoir solution or reservoir model that's going to answer all of these same questions. Some of these questions deal with problems at different scales. So the basic process is to develop a stratigraphic model, use a stratigraphy to create a structural model, and then use the structural model in your well logs to create a 3D grid of the appropriate scale, develop your facies and propagate your petrophysical properties nested into your facies models, and then finally cut and slice and dice for sector models or geobody mapping as needed. So obviously this is kind of a gross oversimplification, and a few of these can occur concurrently. So the stratigraphic model is made of well top picks and maybe some seismic stratigraphy and should be consistent to your depositional or sequence stratigraphic model. Some petrophysical logs and facies analysis can be done while stratigraphic model work is being completed, but often it needs to wait until you have final zones and thicknesses to pass along. So the grid size needs to be determined in order to build the structural model, which means you have to analyze some of the well logs that you might not have all of them ready yet. And the cell height needs to be settled before well logs can be upscaled to the 3D grid. Variogram analysis and vertical proportion curves for facies properties need to be completed before your petrophysical property distribution, and finally sector model cutting. So again, all this is a kind of a gross oversimplification of the petrophysical model development, which is its own iterative process. None of these steps stand alone. Need to be kind of working in a multidisciplinary team. And specifically when you're working with your petrophysicists, we want our logs like the way we order our fast food. We want them fast. We want it in an LAS format. We don't really care how long the logs were cooked in the kitchen. This is kind of the wrong approach. Everyone should be iterating on processes and going back and forth and understanding, what are the assumptions that are going in and out of the model. So the examples I'll show today are from both the Midland and Delaware basins, and we'll kind of hop back and forth between the two. So a quick view of the basin in cross section. The Delaware Basin is much deeper into the west of the Central Basin platform than the Midland Basin. The Central Basin platform sits significantly higher, and both the Midland Basin and Delaware Basin are more structurally complex. Closer to the edges of the Central Basin platform, there's also some pretty big structural features that we'll see in the Midland Basin and in the Delaware Basin. Next, we'll take a look at the Delaware Basin side for structural framework. So the previous picture is a nice overview cartoon of the depositional and structural models, and this is what it might look like in more practice. It's a little more complicated. So I am showing an example well log from each county in the Delaware Basin with gamma ray, resistivity, and neutron log tracks. I'm also showing the section from the Avalon to the Strawn section, which is about 5,000 to 8,000 feet of stratigraphy. It's a lot of rock to characterize. This model uses a stratigraphic sequence breaking the section into 11 units. And a quick look at the section shows that the thickness and composition of each unit is changing throughout the basin. For example, the Wolfcamp C has a dramatic thickening in the central part of the basin and thinning to the basin edges. And these are some of the factors that you need to consider when choosing what your model area might be, what your model cell size and thicknesses should be. So from this bird's eye view, that's about all we can tell, but there are some other than there are some clearly more compositional and thickness changes we need to account for. So after you've picked all your well tops and you have a structural model, you can start to build your 3D grid maybe and take an initial look. So this is the structural framework and expanding across the basin model area. You can show a fence diagram. In this particular diagram, I'm showing zones by color. We can see the structural complexity against the central basin platform to the west, and the thickness changes across the basin, especially in these pink and purple units, and the faulted nature at the base of the model in the expansion of the Wolfcamp C section. So popping over to the Midland Basin side. Uh-oh, I might need help. I need my cursor back to play the video. There we go. All right, so popping over to the Midland Basin side, once you have your stratigraphic model and tops picked for your data set, you can begin your structural model. The Midland Basin model is, I'm just showing 3 of our 11 horizons. You can see the prominent nose highlands, the high section in red, that's present in the upper and middle horizons that I have shown, but not that lower section. So we're clearly capturing some thickening, thinning in the section. This data set had about 1,800 structural data points to create this data density and capture these features of the basin. So we're imaging the Big Lake Fault in the south, but we're not modeling it as a fault. We're also capturing some of the structural highs in the southwest. We're not specifically incorporating the faults because that's not really the purpose of this model, as the purpose is really to capture trends, property trends specifically in petrophysics, and to use for sector modeling and reservoir stimulation. So a large fault in a low priority zone really doesn't add value to the model in this particular time. It's not that we can't include it, it's just not, it's not a priority at this point. So we need to consider the types of data and data density and what types of variables we're including. So we need to understand our discrete and continuous species or continuous variables. Continuous variables are petrophysical properties like depth. For example, any number between 0 and 1 is a valid percent compositional measurement, or take depth. To get to 0 to 100, you have to pass through every incremental number in a continuum. So at some point, for example, you'll pass 50. Discrete variables are facies classes or properties that can't be interpolated into smaller units. I think of it like a stair step. There's nothing in between your stairs. You jump from one level to another. Colors, species, classifications are all discrete variables. Cell area needs to be determined by data density at the scale and rate at which data changes. Cell size should be small enough to have only one well per cell contributing data. If you have a smaller than that or a larger than that cell size, you're losing scope of your well logs, and you're having multiple data points in the same cell averaging on your data. Your cell size should be small enough to have to reduce computation, or sorry, large enough to reduce computation time, and small enough to have multiple cells between data points, enough to interpret a gradient if that needs to happen. So to kind of illustrate this concept, I have an outcrop model that can be interpreted into 3 units with porosity measurements and how porosity will change in the outcome model if modeled as a continuous property or nested into a discrete property like a facies. So the discrete method, so we have this outcrop. I have a sandstone 1, a shale 2, shale 3 with measurements. We have very high porosity in the sandstone, medium porosity in shale 2, and low porosity in shale 3. If we model them, so the discrete method breaks it up into 3 units, allowing for a sharp step change in porosity between sandstone 1 at the top and shale 2. Modeling continuous porosity will insert an erroneous zone of high porosity in between sandstone 1 and shale 2, because you can't go from medium to very high porosities without stepping through that high porosity zone first. So this is just a really basic cartoon example of a facies interpretation based on outcrop and observations. Assigning facies classifications to your data set usually involves a much deeper dive into your data trends. We use machine learning methods to segment the reservoir into zones consistent rock properties based on logs. We develop facies specific to the different domains, either petrophysics, geology, rock quality, geomechanics, while integrating data between the disciplines. Geological and reservoir quality facies are developed using core-tied petrophysical models specific to each formation in the model. These facies are developed with machine learning algorithms. This is what Dave talked about last week, to provide input to our reservoir simulation models. We use ML to create both high and low tier, or to utilize both high tier and low tier logs to create consistent data sets, coupled boundary models that can be universally applied within the model area. So the resulting classes also, those still have to be QC'd. This is not a hands-off process. This is very much a hands-on iterative process. The interpreter needs to be making a designation of what classes can be lumped or split based on the needs of the model and what's appropriate. So an example of the 3 facies classes that we like to use are geofacies from core-tied petrophysical models with quartz, clay, carbonate, and pyrite. Reservoir quality facies might include porosity, kerogen, clay, and resistivity. And a production quality facies might be a cross-tabulation of the two while pulling in maybe some reservoir engineering data and core porosity-perm relationships. So during Dave's presentation last week, there were a few questions on upscaling well logs and the impact of that model. And we have looked at this briefly in the simple outcrop data cartoon model, but in a real model, cell size is determined by both quantitative and qualitative methods. Vertical cell size and upscaling are the same issue. Your vertical cell size changes the outcome of your upscaled well logs and therefore the outcome of your reservoir simulations. Quantitatively, we can use a vertical variogram to look at how a log, in this case porosity, changes vertically and choose a determination point for cell size at the sill and the matching vertical range. So this is the distance from the original point where data is no longer related to the original point. In this case, the vertical variogram model is shown for one formation, a Wolfcamp A, along with a log clip of a Wolfcamp A showing gamma ray, resistivity, neutron density, and then overlying the along with porosity on the right hand side there. So overlying the porosity curve is an upscaled block well curve to the 4-foot cell size that we observed that we took from the variogram analysis. So, and then last but not least, we want to make sure that distributions of data are not changing between the open hole log and upscaled well log. In this case, we can see that the pink bars, which represent open hole logs, have higher values, and they're not really being captured in the upscaling. This is usually something to do with bed thicknesses, and that your very high porosity beds are usually much thinner and more isolated than your low and average porosity beds. So bed thickness is not an evenly distributed attribute. So is there anything we can do to fix this? And the answer is yes. We have to use some interpretation, and we can change the way that we upscale our facies logs or upscale any log. But we're going to take a deeper look at facies distributions. So in this particular model, facies 14 is a high value priority facies representing the highest porosities and permeabilities. Facies 12 and 13 and 14 are also very related and have resulted from splitting up of what used to be one class into 4, the original, and then facies 12, 13, and 14. So that's important context to keep in mind when we're making some of the alterations, and it's very model and zone specific. This is not something that you can just code or pop out of that will pop out automatically from any algorithm. So we use a most of algorithm for upscaling discrete data, which simply counts the number of classes per cell and assigns the class that has the highest number of counts. Upscaling the new facies classes to the model scale has resulted in a slightly lower abundance of that priority facies 14. 14 exists in thin beds, usually below the model resolution, and ends up being washed out in the model. And in this case, we want to apply a specific porosity permeability trend. So it's a high priority, something the reservoir engineers are interested in. So it needs to be actually present in the model. It can't be washed out. So let's take a look at just a quick look at why, why is this abundance different? It's because of the bed thicknesses. So we can plot the distribution and observe that most beds of this high priority facies thickness are below resolution of the vertical cell size. So I'm looking at facies 14 across all zones in the model. We can see that the average thickness, in this case, is less than the average cell thickness. In this case, facies 14 is only a priority facies in selected formations, in this case, the third bone sand and the Wolfcamp A, which includes the XY sands for those familiar with the Delaware Basin. And facies 14 is represented in very low overall abundance in other formations and is not a priority target. So the upper chart shows the average thickness across all formations with the table. So, we're looking at somewhere around that 2 level for facies 14, no matter the formation. And then the lower chart shows the distribution specific to the third bone spring sand and where most bed thicknesses plot. Most beds of this facies that is a priority facies, are either that ½ foot, one, less than 2 foot thick interval. And so that's really hard to capture. So what does this actually look like in log form? And again, I have an example from the Delaware Basin, third bone spring sand. And a way to change the upscaling outcome is to apply, different weightings during the process. And we can be weighting logs according to class or another property. In this case, I'm showing the results from multiple weighting options in the log facies tracks. Facies 14 is in black and facies 12 and 13 are in gray. The open hole log shows facies classifications at the ½ foot step. And in the 50-foot highlighted area, we can see that there is a lot of black at the open hole log step, but it's totally missing from that track 1, which is just uses a standard most of upscaling method. So it's missing from the model, therefore it's going to be missing from the sector model that we eventually pass to the reservoir engineers for reservoir simulation. We can apply different weightings to facies 14 and we analyze the outcomes qualitatively and quantitatively with the histogram distributions. So in this case, we select model 5 and kind of acknowledge that the facies 14 will be emphasized compared to log abundances. And again, this is where context matters. This isn't a blindly applied weighting, but it's a deliberate excursion from the input distributions in order to meet the needs of the model to a specific formation and incorporates analysis of bed thicknesses and what we want to actually see in the resulting model. So after the facies are upscaled, we can distribute facies properties in the 3D grid. Facies are groupings that have related data. In these 2 examples, I show geofacies and production quality facies. Geofacies can be grouped into the bigger classes of mudstone, siliceous rock, and carbonates defined by quartz, clay, and mudstone. So in each of these, going to have unique distributions of properties. For example, looking at production quality facies in B and D, I show the porosity distribution below. So that means that for facies B, we have an average porosity of 8 and an average porosity of 0.4 for facies D. But there's some overlap still there. So they're not exclusive of other porosity values in facies B and D. There's a range. So along with porosity, each facies property will have a unique distribution, and it's the overlap and distribution of each class or each part of a facies that makes up, or each property that belongs to a facies that makes up the each property that belongs to a facies makes up the distribution of a facies as a whole. So we model facies so that petrophysical properties are modeled in the domain in which they vary continuously. So for example, back to that cartoon I showed, modeling sand's property in the sandstone across the sandstone, and then allowing a model to have a jump as we move to a different facies where we would not expect a continuous gradient between our measurements, maybe into that shale facies below. So facies are modeled with conditional stochastic stimulation algorithms like a sequential indicator simulation. We use facies proportion maps and vertical proportion curves to create a facies model. The vertical proportion curve shows the abundance of each facies, each layer of the model. This 2D distribution guides the 3D model to have the same proportions. And also use a 2D aerial trend map that ideally shows how facies abundances are changing. Combining the two creates a 3D probability cube to guide the model. You can use seismic volume cubes also for this if trained and conditioned. Those make excellent resources. Petrophysical properties are nested into facies so that they are modeled in the domain that they vary continuously. We use geostatistical methods and horizontal variograms and vertical variograms along with the 2D trend maps to distribute facies with sequential Gaussian simulation algorithms to create probabilistic outcomes. Primary properties that we distribute are porosity, water saturation, clay, and then nearly every other petrophysical property. So what do these results look like? What does this all look like in the end? It's the exciting part. So the end result is a core-tied petrophysical 3D model that represents the reservoir. It doesn't replicate, but it represents the reservoir. In this example above, for the Delaware Basin, we used almost 2,000 wells for structural control, divided into 12 stratigraphic horizons with a subset of those structural wells with core-tied petrophysical well logs and models applied with facies models. The average cell size is about 10.5 feet, and that varies with zone and location in the model. Model covers 13.7 thousand square miles with 400 million cells. This model serves as a subset to cut sector models of any size to pass to reservoir engineering or other colleagues for stimulation or even depletion modeling, like in this reservoir simulation of injection modeling of saltwater disposal wells in an induced seismicity project. You can also pan through the results of a structural model. This result looks at the Midland Basin model shown as the zones. And we can see here the growth of the glasscock nose feature prominently with thickening and thinning of the zones in green. And then as we come off, we'll see it start to thin. And these can be useful for incorporating spatial context into well development planning. Again, we can look at cross sections through the glasscock nose, which is the same feature we just saw growing in the previous slide. And we can look at how those properties and facies vary across sections. So we're looking at Howard County, Glasscock County, and Reagan County at porosity and geophases trends. We can map our carbonates in the geophases shedding off the nose feature into the basin, and more prominently, south into Reagan County. We see how that relates to our porosity trends. We're also picking up deeper features like the Horseshoe Atoll up in Howard County in the Wolfcamp Decline section. A closer look at the well pad level and volume cubes can be analyzed for geobody detection. This view is looking at the well pad level with different filters applied in this case. I show low quality reservoir rock in the blocked cells, but they are colored by geophases. And so we can see the relationship to well placement and the types of rocks that surround the wellbore. Low quality rock is not only made up of the carbonates in this case, but there are siliceous geophases that also still map as low quality facies. And so we can also observe the continuity of bodies of rocks or facies. This is particularly powerful when seismic volumes are used as secondary properties or when there is an abundance of low quality data, like when we have 16 wells per section in the Midland Basin. And finally, we can make any type of map or volumetric calculation. I have different examples here, like if we're interested in carbonates, maybe we can look at the percent of carbonate in a particular horizon. We can look at hydrocarbon pore volume calculations, or simply just understanding or getting a better handle on the structural variations in our specific area. Other products are the Basin Geomodel, SegWi property volumes, sector models for reservoir engineering, petrophysical property maps, volume calculations, geobody connected volume identification, log extractions. We can update models with relative ease to incorporate new drilling tops, and models can have saved workflows in order to incorporate new logs easily. And even new zones can be added with relative ease and slotted into an existing framework. So up next is Dario with more on how we use the models in the reservoir team. Thank you.
Hey, thanks, Katie. So, yeah, Dario, if you can pick up your screen share and start with yours.
Okay, will do. I assume you can see my screen.
Got it. Looks good.
Great. Well, thanks everyone. I appreciate the opportunity to try and tie in all of the stuff that we've talked about in the last 3 weeks with Dr. Don Hayes, Dave Handwerger, and then what Katie showed today. So this is by no means an exhaustive view of what a completion engineer might do, nor what a frac engineer would do, but I did want to try to tie in for companies that are trying to understand why some fracs work, why some fracs don't work. I want to show some of the things that we look at to help guide that way, and to use these geomodels to help guide what a frac engineer might do. Okay, so this is a process that's put together by Premier Corex. So last week was Dave Handwerger talking about data science, doing the spatial modeling, getting all your data together. We talked about petrophysics. We talked about geology. Today, Katie showed the geomechanics and putting all this together into a geomodel, and how this all then ties into completion modeling and what we can do with this data to help us guide what our frac models should look like, what we can do to improve them going forward. So here's a representation of various stages in a well. This is not a real well, but what I've done is I created a horizontal well that's tilted, coming in through one part of the formation, and then dipping down below the primary oil target. And the purpose of this is to show what happens when you potentially go high, you come down low. We know that the rock is not a nice flat layered surface, but sometimes you'll be into tighter rock, lower porosity, higher porosity, etc. So what we've got is the wellbore, the primary oil target. What we've got in the vertical columns here are all the different layers in the model, and the colors are really the type of formation. So the blue, both above and below, are water bearing. And this client had an issue. He had 6 wells that he drilled and fracked, vertical wells. 5 of them produced mostly water, almost no oil. 1 well, for some reason, even though it's screened out, produced a good volume of oil and no water. And we were trying to understand what's happening here. Is there something in the design that we can alter to help with the production? So let's go look at this as this will start to rotate. You'll see this is up high, this is low in the formation. I'm going to stop that. You can see as you dip down below the primary oil target, the frac actually wants to grow downwards, and it does connect into this water bearing zone. So here's a first, and this is with cross-linked fluid. This was a cross-linked fluid frac that we looked at. And we do see that it connected down below into the water. As we continue to rotate this, oops, sorry. Let's continue that. So as it starts to turn, you'll see that here, as we go down, we've got down into the water. And as we get up to the top, above the actual oil zone, we see that the frac is actually wanting to grow down into the oil zone, but we don't have a good connection at the wellbore. So when we look at, and this is a peculiar case where they're doing single cluster horizontal wells, although the 5 they've done are vertical. So this is what I call a landing study. This is looking at putting perforations in different layers to see how the frac grows. And so this helps them understand where the optimal landing is, and hopefully the drillers can keep us in that position. So another way to look at this is to create pseudo landing zones. And the reason I do this with steps is now I can actually put in more than one cluster. I can put in more than one stage to see how interstage, intercluster frac height might be, how it differs as we go through various landing points. So I'll just let this rotate. You'll see that up high, it's grown up into the water. You get down, it goes down into the water. And so this is just a quick visual to help us understand where the best landing zone is. And then the nice thing with frac models is that you can run multiple iterations very quickly. You can change so many different variables to help you understand how those variables might alter the final frac geometry. And when you get wells that don't produce the way you want them to, you can look at these things and zero in. So what we did zero in on was that 5 of the wells had cross-link fluid used, and it connected both water above and below. They did some water analysis, so we know that they got immense frac heights. The one well that didn't, we found out later, turned out to be a linear job because they couldn't get the gel to cross-link. So it was linear and it screened out early, and that frac height stayed within the zone of interest, and so no water. So at the end, what we're trying to do is run multiple simulations, and we can do hundreds of these very quickly, and it's a lot cheaper and a heck of a lot better than running iterations in the field. And with that, that's really all I wanted to say. It was just trying to tie in the subsurface and how we should be using this data, even in data areas where we don't have a lot of data, where we can come to companies like this, get that data, and actually create frac models to help us better the final design. Thanks, Steve.
Hey, thank you, Dario. I think that's a great example, and it's also a pretty picture of what you can get as stim plan output. So, as I think about this, the geomodeling is, a lot of us are, I have a bachelor's in geology, so I can tell geologist jokes. But, a lot of us think about geologists as being out there with a rock hammer and, drawing colored maps. And, but really what Katie's showing is how this geomodeling becomes our spatial database for the reservoir, not just for the rock fabric, but also, as Dave talked about last week, for the contents of the porosity, and then how that behaves as a bulk material geomechanically. So, these geomodels are really valuable, and I know these ones that Katie shows are just examples of what Premier has done in the Midland and Delaware. And, those took a couple of years to create, and, millions of dollars of data was integrated into them. So, this is not a trivial endeavor to create these models, but, once you have them, they're, as Dario can attest to, they're just super valuable. And a couple of, as I kind of think about this process, we start out with dawns of what's really going on with the macro geologic environment. What's the macro depositional environment, so that we can keep true to what we understand is going on in the reservoir. And then using the machine learning that Dave has developed, how you can make a robust linkage between what you get with the logs and what you get with the laboratory. And then, because that's very often not that's a non-trivial endeavor to make that linkage properly and robustly. And then third, what Katie has shown is pulling all that together and using these spatial algorithms, variograms, to be able to extend and interpolate between the hard data sets that we have to then create a more nuanced, as she said, a representation of the reservoir, and how that can then, when you have all that together, how you can cut and paste from it to get the inputs you need to properly engineer the completion. And Ron made a comment here that he beat me to the punch that, you know, when you think about what we're doing in these unconventionals, where we're doing completions, you know, we're drilling wells that are 2-3 miles lateral, and to assume that it's going to be a layer cake from heel to toe is just irrational. And so, you know, as Ron said, we're seeing a lot of different fracture growth behavior along the path of the well because, you know, the geology is changing. And, you know, with Katie's geomodel, which, you know, these are pretty detailed, robust models, you know, she's got something like 60 cells per section horizontally times, you know, X number of layer cells. So per section, you've got, you know, hundreds of cells that you've got information about what's going on with that bulk rock, which you can then, as Dario showed, you've got different levers you can pull for how you're going to complete that. You know, what do I want to use for viscosity? What do I want to use for rate? What do I got for density? You know, the engineering levers we can pull to manipulate how that fracture behaves. And so I think that's really, you know, where we try to get with this is how do we develop the information that we can then utilize to manipulate the reservoir to achieve the fracture geometries that allow us to drain the reservoir most efficiently. And there was another question from Ted that Katie already answered, but I'll make a comment on that. The seismicity example was a study done for a small group of a proprietary study done for a small group of operators in the Midland Basin, but the you know, the workflow, the analysis for that is something that, you know, is available. So let's see if there was anything else that had come in. So I think on the Q&A that was kind of it. And you know, so I guess, you know, Dario, I'll kind of open it up to you again of, you know, you showed this example from you know, dealing with trying to optimize the landing of the well, but as Ron points out, it also helps you think about how the reservoir might be changing along the well and whether, you know, you're going to run into challenges, whether you need to engineer the completions as you go along the well versus just have the same design from heel to toe. So I don't know, Dario, if you wanted to make any comments about, you know, the pros and cons of trying to engineer completions versus the operational simplicity of just saying, hey, here's our design, we're going to bang it out from heel to toe.
Yes, I've got a bunch of comments there. So for sure, the geology is changing along that wellbore. I think Katie did show some good examples of that spatial difference along a wellbore. What's nice with what they've created is you can take slices anywhere along that wellbore, get those properties, run a model through it, and get what, you know, again, go through all the variables and look at what that frac geometry might look like. In terms of engineered designs versus, it's a double-edged sword. You go to engineered completions, they can certainly lead to a lot longer times between stages, you're changing guns, you're changing a lot of things. Most field guys like one program, everything is the same, and you just repeat, and that's where you get your efficiencies. If you're fracking one well a year, 10 wells a year, you know, I would definitely look at engineered completions. And even if you're fracking thousands of wells or hundreds of wells, it's probably worth looking at and just seeing if there isn't a way, looking at the variability along the wellbore of how you could cluster is probably the wrong word, how you could group those clusters in a more engineered approach where the geology is more similar. But again, it's got to be tempered with operations and the inefficiencies that you get when you change gun lengths, gun sizes, and so it's a double-edged sword, like I said.
Katie, there's another, Gianni has a question here, which I'm not going to even try to understand of.
Yeah, I'm thinking about how best to answer this question, Gianni. So a lot of that work falls into, I'm thinking the petrophysical side, and we didn't really particularly have that data to go into this model. So the simple answer is that I didn't correct for any of that for diagenetic overprints or, you know, concretions and cemented layers. But we definitely can. It just takes maybe a little bit of a different input data. So you have to be able to characterize that somehow. Maybe that's, you know, if you have a core description and you're incorporating core facies, rock fabrics into your facies logs, that is something that you could deal with. Maybe you see the concretions and cemented layers better from your image logs. You know, those are things you can incorporate, but you have to have them to be able to incorporate them into the geomodel. They're never just gonna come out unless they were specifically addressed in one of the inputs, maybe in the petrophysical model or in a facies classification.
Steve, this is Ali Donashi. Just a question, you know, one of the more important parameters in fracturing operations are the stress directions, orientation of stresses and so on. And how do you model the stresses, and how do you get the data and the input in order to integrate it into your structural model?
Yeah, that's good, Ali. I mean, you know, typically what you end up with in these mechanical models is really kind of a one-dimensional model, but the overlay of building a three-dimensional mechanical model is what we've been working on. And, you know, how you get the data from that, it's like all of this stuff, you know, again, this geomodel is a data repository. It's from wherever you can get it. You know, if you've got someone who's done some type of stress analysis that you think is worthwhile, you can try to build that into your model. And as Katie said with the diagenic stuff, it's, you know, if you have the data and you can make a robust correlation with the petrophysics or with the lab data, then you can start to incorporate it into your model. And, you know, but it, you know, yeah, the stress direction is, you know, really important, but I'd say for a lot of the basin, it's, you know, it's kind of assumed as opposed to measured. I'm not trying to dance around it, Ali. I'm just saying, you know, that all that stuff can be incorporated, but for what we've done here so far, that's not been a big part of the data set.
So in the Delaware Basin, from the maps I've seen of, you know, principal horizontal stress, it is not one direction. It depends where you are in the basin, and it'll even change through production and, you know, wherever the primary wells are and secondary wells. And then, of course, you've got your lease lines, which go in strange directions. So it all comes into play, and it's all stuff that has to be looked at. not an easy one.
Very nicely said, Dario. Exactly.
Yeah, and again, what we're showing is just an example of a workflow that was utilized to create these particular models. And this workflow can be adapted to any reservoir. And some reservoirs where, like I think of one in Indonesia in particular, the tectonic stress field is very complex, and it becomes more, understanding it becomes critical to successful fracturing. And in those instances, that would be a case where you'd really put energy into trying to build that into your model. So, again, I think what Katie has shown and from the previous weeks is, really just given an excellent example of how this workflow can be used to develop this tool that, if understood, if you've got it and you understand it, you can really improve what you're doing with your completion engineering, with your modeling and how your completions are going to, drain the reservoir, which of course is what it all comes down to. So with that, we're actually after 10 o'clock. I'm sorry we ran long today. Dario, I guess I'll take it back for a second. And just remind everybody again that next week we've got Stacy King doing something fun with our Let's Get Astrophysical. And so I hope everybody can join us from that. I think it's going to be really, really cool. And I really would recommend, people invite your family and friends, because it's going to be entertaining and informative. And then finally, as always, if we're like I said, 2 years and 8 months into this, and we wouldn't be able to do it without the support of our audience. And so anybody who's interested in being a speaker in a future session, just let us know. We'd love to work something out and have you participate as a speaker. And we love the Q&A that comes in. So again, without the audience inputs here, this just wouldn't be nearly as much fun. So with that, thank you, Katie. Really appreciate it. Thank you, Dario. And thank you to our audience. Have a great week and be safe.